Hello everybody, welcome to Penno's Philosophy. I am TJ, and today we'll be talking about black holes. Let's start out what a black hole actually is. So, in my last video I mentioned that when a star that is just about as big as it gets, a lot bigger than our sun, has a supernova, all of this mass pushes to the center, and it's so much power that it compresses to a singular point. Zero-dimensional, zero width, height, depth. I mentioned what the zero dimension is in my first video. Let's take a look at the parts of a black hole. You might have seen in a lot of representations or diagrams of a black hole, there's a colorful ring around the edge and through the middle. This is the accretion disk. It's a lot like a ring around a planet. Now it'll look like there's two rings, but in reality it's only one. And the reason it looks like there's one around this way is because the light of it gets bent around to the edge. The light of the back of the disk gets bent to the edge of it. So when you see this, you're looking at the back of the disk. Inside here will be that entirely dark, empty void. And then, of course, the singularity, the infinitely dense point. The part where everything is being absorbed into. These will exist for an incomprehensible amount of time. They will be one of the last things left when the universe ends. And it may seem like they're some kind of hungry giant that's eating all the time, but in reality it only takes in about 40% of what it pulls, and the other 60% it either spews out as jets or turns it into light. And the light that it produces is why the center of each universe is so bright. So, a black hole, when you look at it, it's a large, dark mass. When they say a black hole is however wide, they're measuring the event horizon. The event horizon is the point of no return. At that point, not even light can escape, which means it's entirely black, or at least appears entirely black. We perceive things because light bounces off of it and then hits our eyes, and then we take that information in and turn it into objects. But when light goes into the black hole, it doesn't come back. So there is no light to perceive. So it's just black. And they are so hard to see because there's not much comparison between a black hole and the surrounding area, because space is black. So they use X-rays to find them. So imagine what a black hole would look like on the inside. All of this light and anything else is attracted to the singularity, which has so much mass condensed infinitely. Let's imagine what it looks like on the inside of the event horizon. You would assume that inside here, since no light can escape, it's entirely dark. But watching a movie called Interstellar, the main character falls into a black hole, and on the inside it isn't entirely dark. In fact, there's a good amount of light in it. So just because light can't escape doesn't mean it's entirely dark on the inside. So you might be able to see things falling in when you're on the inside, but most likely it's going to be distorted and confusing to look at because the light is bent. So the inside could look like anything, but it would likely be very dark because if light does bounce off of something, it's not going to be easy coming to your eyes. So vision will be delayed, and when you do see something, it'll probably have different colors, different shape. So let's take an example. Take a scenario. So let's say you're in a spacecraft approaching a black hole. If it's on the smaller scales of black holes, then the distance between the front of you and the back of you is going to be a very big difference relative to the singularity, which is the center of it. Which means if you're falling feet first into it, your feet are going to be pulled so much more than your head, which means you'll be pulled apart and stretched in a process called spaghettification. Not a good ending. But let's say you're approaching the black hole from Interstellar, Gargantua. Gargantua is so big that distance of your head and feet relative to the singularity isn't much difference, so you won't be pulled apart, but as you're approaching, this will be a large dark mass, and you'll see it appear to grow as you approach it, as all things do, but then it'll become the horizon, and then it'll stretch past the horizon. So then the outside, all you can see is a circle that is shrinking. And as you look through this circle, you'll see the rest of the universe speeding up at a very fast pace, and you'll see it end. And as that circle shrinks more and more, you look back forward, and the ship around you, any blinking lights, any vibration, any movement in the ship, your vision will be delayed, and you might be able to see surrounding dust and whatnot around you, and you probably won't be seeing much light around you because it has nothing to bounce off of, so it's only going to the singularity. So it's going to be mostly an empty void. Another effect that black holes have. It's so incredibly dense that it bends space-time by an incredible amount. You might have seen diagrams of something like a star bending space-time. It might be about this much with the star, but with the black hole, it's infinitely dense, so it bends a lot. Something like that. So as you approach at the event horizon, space and time start to switch. Right at this point, they switch about 45 degrees, and then as you approach, it gets more and more switched. So, to you, the outside world is going at an incredible speed, ending, and you are moving at impossible speeds, yet you're moving slower. You appear to be moving slower the closer you get to the singularity. But let's say somebody else is watching from outside. They see you get closer to the darkness and then fade away into it. The fading starts fast and then it slows down, and you'll be left there for millions of years, at least from what they can see. Let's say a black hole about this big appears directly in front of you. Imagine hypothetically the only thing it can pull in is light, so you won't get spaghettified along with whatever's around you and the planet. So all you see is a confusing, empty void, seems like. It's like a hole in reality, and light is bent around it. So the very edge around it is a little bit distorted, a little bit confusing looking. Let's say you try and touch it. Something called Hawking radiation makes it a little bit warm. The biggest black holes only produce a little bit, but the smallest ones produce a lot. So if you touch it, it would be pretty warm, but you could go right through it because it's empty space inside. Perfect vacuum. And if you try and touch the singularity, you can't. The atoms of your finger don't even compare to the infinitely small size of the singularity. So your fingers would go right through it, or it would go right through your fingers. It'd be like there's nothing there. So touching a black hole would feel entirely empty and just warm. Even if you had something that was much smaller than an atom, if you shrunk down to the size of an electron, it would still be the same. Zero-dimensional is infinitely small. If you could look inside a black hole and you could perfectly see everything inside, you still wouldn't be able to see the singularity. So in a game I've shown in my other channel, a pretty good representation of what a black hole would look like on the inside is that, minus the purple. You see, if
there was, if light did go back to your eyes, there's nothing for it to bounce off of. It's entirely empty besides the singularity, which light is too big to bounce off of. Singularity is so incredibly small that light just passes right by it and it can't reflect off of it.
I'll be linking a video that has a lot more details on how big a star needs to be to turn into a black hole and other details like that. If you've enjoyed, like, subscribe, share with others who might be interested. Check out all my other stuff on both my channels, and I'll see you in the next one.